Hey guys, welcome back. I'm going to finish up this part of the drag problem and continue on to our other ones. So they asked us to graph it, and we want to have a linear graph. And we picked that we were going to have either mg or m on the y-axis, and the x-axis was b squared, t squared. All right, so my weights go from 1 up to a little bit more than 5. So if I make each one of these 1, 2, 3, 4, 5, 6, if I make each one of them 1, 2, 3, 4, 5, 6, and then because it's times 10 to the negative second, up here I'm just going to put times 10 to the negative second. Here I'm going to say this is mg in newtons. And you can always do this if it's easier, and that way you don't have to worry about exponents or decimals. Along the y-axis, along the x-axis, it goes from 0 to about 1.1. So I have 1, 2, 3, 4, 5, 6. So why don't I make this 0.25, 0.5, 0.75, 1, and 1.25, and then my last point's going to end up being here. So I'm using most of my graphs, and that's what they want you to do. And I'm going to say that this is bt squared in meters squared second squared. All right, so I'm going to plot my points. I'll try to do the best. The smartboard's not as toned in on this. So it's 0.26 and 1.1. And then it's 2 and 0.38. And then it's 3 and 0.67. And then it is 4.2 and 0.85. 0.875 would be the middle of this whole thing. A little bit flat into that. 4.2 would be that line. And then 5.1 and 1.12. That's right dead in the middle. So it looks like, remember I said that you could do just graphing m? It looks like if you graphed mg, things, well, I guess if you graphed m too, it's just multiplying by 10. All right, so I need to do a best fit line. And I set this up so my slope would be c. Very often, if they have you graph things, if they pick it, you're going to have to take your slope and then take the inverse of it, or take the slope and divide it by something, or take the slope and multiply it by something. That's typically what they have you do. All right, so I'm going to pick 2 points that are not my points, that are on this line. I'm looking for right where it crosses. They're also supposed to be far apart. That might be the closest that I have there. All right, so this one would be 0.15, comma, 0.8. And this one would be 1, comma, 4.8. And so C is going to be equal to my slope. Again, there's often points for an equation, so you want to actually write down the equation of slope, and you want to put in values with units. I don't know why I wrote down this, because this is newtons, right? This one is square and second square. All right, I have a calculator next to me. So I got 4.7 newtons over meter squared second squared, which I'm sure that we could simplify the units of, but I'm not that interested in that. A particular stack, so like we calculated C, a particular stack of filters with mass m is dropped from rest and reaches a speed very close to terminal speed by the time it has fallen a distance y. Sketch the approximate graph of speed versus time from the time the filters are released up to the time t equals t that filters have fallen a distance y, indicate the time t equals capital T and terminal speed. So we're going to go to a terminal speed. It's going to be a curve because the slope of velocity would be acceleration, and the acceleration is always changing. It's related to your speed, right? This is going to approach that line, and we're going to put T on here. Suppose you had a graph like the one sketched in C that had a numerical scale on each axis. Describe how you could use the graph to approximate the distance. To get distance from this, we would take the integral of the function or the area under the curve. So again, we're using the same skills we had prior. We're just including calculus in. All right, so a ball of mass m is thrown vertically upward with an initial speed of v naught. It experiences a force of air resistance given by F equals negative kV, where K is a positive constant. The positive direction for all vector quantities is upward. Express in algebraic answers in terms of M, K, V naught, and fundamental constants. Does the magnitude of the acceleration of the ball increase, decrease, or remain the same as the ball moves upward? So our acceleration is going to be related on our forces. Both of our forces, as we go up, are mg and kv. I don't have to write negative kv because I drew it down. So if we think about this, mg is going to be constant. So its portion of how much it contributes to the acceleration isn't going to change. As I throw something up, though, this one is a function of speed, and that's going to get smaller. So that would mean that our acceleration would decrease. And I would justify that by one part of the net force being a function of velocity. Write but do not solve a differential equation for the instantaneous speed of the ball in terms of time as the ball moves upward. All right, so we're saying that F net is equal to MA based on the free body diagram that I drew. This is going to be negative mg minus bv is equal to MA. Again, as is the case with all of these problems, they want you to express acceleration in terms of velocity and its function of time. So I would write this as minus mg minus bv equals m dv dt. And then I need to get dt to one side and my v to the other. So I'll get m to the other side too. So I'll have dt over m. And why don't I take a negative out of here? And then on the other side, I will have dv over mg plus bv. And I will integrate this from 0 to t, and I'll integrate this from 0 to v. So sometimes they'll just want you to set it up. Sometimes they want you to solve it. Again, it's a time thing. Because as we're going to see, the actual solving gets a little cumbersome, which we'll be going over in the next couple slides. Terminal speed is when Fnet equals 0. So for our terminal speed, you would have minus mg minus bv is equal to 0. And so we would have bv is equal to negative mg. And so vt would be equal to mg over v. And very often they ask you what that is. So even if you're not totally comfortable with the calculus part of it, which I know is going to have a lot of steps to it, the terminal speed, we just get to realize, and we talked about terminal velocity, we just didn't do the math involved with it because it required the natural log usually. Does it take longer for the ball to rise to its maximum height or fall from its maximum height back to the height from which it was thrown? So on the way up, this is our function, our free body diagram. On the way down, this is our free body diagram. On the way up and on the way down, our system is losing energy. So that's what this drag force tells us, that we have this non-conservative force that's friction. And so because it's going to be losing energy all the way up, on the way down, it's not going to reach a velocity anywhere near the original velocity it took. So it's going to take longer to fall down because of this non-conservative force. On the axis below, sketch a graph of the velocity versus time for the upward and downward part of the ball's flight, where TF is the time at which the ball returns to the height at which it was thrown. So we're going to have, we're saying that it's going to take longer to come down than it did to go up. So we're going to have to mark our 0 position. It doesn't matter where it is, but it needs to be before the halfway point, right? So why don't we say this? And then whatever this velocity starts with, let's say we started there, this one needs to be less. And then this is going to, as we go up, our acceleration needs to decrease. That's what they told us. So that means I need to start with a steep curve and go to a less steep curve. Then, on the way back down, our acceleration, because this is going to be 0 to start with, is going to start at g, and then as it gets faster, our acceleration again is going to decrease. So I need to go to start with a steep and go to a less steep curve on this side too. I think that's it on the slide. Yeah. All right, this got all messed up on the choices, but move this down to the glare, right? All right, so an object is released from rest at a time t equals 0 and falls through the air, which exerts a resistive force such that the acceleration a of the object is given by g minus bv, where v is the object's speed and m is a constant. If limiting cases for large and small values or t are considered, which of the following is a possible expression for the speed of an object as an explicit function of time? All right, so So we're going to integrate completely through this. So I'll take you through the steps. First thing I'm going to do is I'm going to express the acceleration as a function of velocity with respect to time. And we're saying that acceleration is the derivative of velocity with respect to time. Then I'm going to get this to this side and dt to the other side. All right, so I don't want to integrate this, so I'm going to do a u substitution, and I'm going to let u equal g minus bv, and so that's going to mean that du is going to be equal to minus bd. And so that means that dv is going to be equal to du over minus b. And then I'm going to substitute this back in. And so we're saying dv is du over minus b. We're saying that this is u. That is equal to dt. I'm going to put my negative b on the other side. So I'm going to have a du over u is equal to negative b dt. And then I'm going to integrate each one of these, and I can leave the negative b out front because it is just a constant. And the one thing I've noticed from doing this for a number of years is that one of the things that makes the calculus students uncomfortable in the physics thing is that we have a lot of constants, and you guys are used to just having numbers. And then any variable you have, you can integrate. And in this, there's a lot of variables that you can't integrate. All right, so I'm going to go from, it's from rest. So I'm going to go from 0 to v, and I'm going to go from 0 to t. And so the integral of this is going to tell me that I have the log, natural log of 0 from 0 to t, and I'm going to have negative bt from 0 to t. All right, so then I'm going to plug back in my u. So let me do this over here. So I'm going to say that I have the natural log, and I made u equal to g minus b. And this is going from 0 to b, and then this is going to just be equal to negative bt, because when I put a 0 in, I get nothing. All right, so I have the natural log of g minus bv minus the natural log of g is equal to negative bt. And that's another thing with this is the rules of natural logs. When we subtract natural logs, it's the same as dividing. So I can write this as natural log of g minus bv over g is equal to negative bt. You can see how cumbersome this is. All right, so to undo the natural log, we use e. So I'm going to use e on each side, and on one side I'm going to get g minus bv over g. On the other, I'm going to get e to the negative bt, and then I'm going to try to get v by itself. So I'll multiply both sides by g. And then I'm going to add bv and subtract ge to the negative bt. And then I can divide out the B, and so I end up with G over B times 1 minus E to the negative BT. In a lot of these, you're going to notice a pattern of like how this shows up, like what it looks like, and that's why they'll make you show all the steps of calculus, because you can go just from, for this the multiple choice, which I don't know if there's any choice that's anywhere close to this, but that's what the answer would be. It looks like that one's the right one, right? Based on what they gave us with the A. But again, we'll do it in steps, and I'll show you that. They don't always ask you to differentiate. They don't always ask you to do all of the calculus stuff. They'll always ask you for a terminal velocity. They'll ask you for graphs. There's a lot of ways to get points if you're a little bit uncomfortable. I know this is one of the more difficult integrations that we're going to have to do. All right, a block of mass M starts at rest at the top of the inclined plane of height H and shown in the figure above. The block travels down the inclined plane. And again, you're going to see that they use a lot of the diagrams. These are different problems. They just change things just slightly. Smooth horizontal surface. While traveling on a horizontal surface, the block collides and attaches to an ideal spring constant K. There's negligible friction, so we just have conservative forces. Spring has negligible mass. I want to know how fast it's going. All right, so I want all of my points. So the first thing I'm going to do is write that energy is conserved, and then at the top I have potential. At the bottom I have kinetic. So I'm going to say mgh is equal to 1/2 mv squared. I'm going to cancel out an m. I'm going to multiply by 2 and square root. And I'm going to make sure that I'm using the letters that they said, and they said H and not Y. Is the speed halfway down the incline greater than, less than, or equal to 1/2 the speed at the bottom of the inclined plane? So when it's halfway down, it has half of the energy. So when it's at halfway down, half of its energy is potential energy, half of its energy is kinetic energy. I'll move this down a little bit too, so it's not clear. So, but does it have half of the velocity? Well, is the energy directly related to velocity? No. Energy is directly proportional to the velocity squared. So let's say that we have 2 joules at the top. And let's make our height 4. So when I'm all the way at the bottom, I'm saying that I have 2 times 10. Actually, I should see what this energy is and then make that the energy. And let's make this, so that's going to be 80. I want to pick something, let's make the height 1. No. Oh, that's fine. So I'm going to make the height 1. And that's going to tell me that my speed at the bottom is 4.5 meters per second. So let's make the kinetic energy, let's make it 1 kilogram. And this gives us 10 joules. All right, so for this mass, what would 5 joules be? 5 joules would be 3.1 meters per second. So I would have 5 joules of kinetic energy halfway down, but I would have more than half of the speed. Derive an expression for the maximum compression of the spring. So this would be mgh equals 1/2 kx squared. Again, we need to do the me naught equals me. You get points sometimes for recognizing the situation you have. And so in this case, I would say that x is 2 mgh over k square rooted. I don't think I'm allowed to express it in terms of velocity, so I couldn't use the kinetic energy equivalent for this. Determine an expression for the time when the block collides with the spring to when the spring reaches its maximum compression. So this is the block hits the spring, the block compresses the spring, the block goes back to where it is. The block is going to stretch past that, right? Because it's going to have that velocity going in the opposite direction. The block comes back to our distance where this is. So this is what t represents, the moment from there to there. So I need to divide this by 4. So it's equilibrium to compression, back to equilibrium, that would be half of the period. Stretching out would be 3/4 of a period, back to equilibrium would be a whole period. So you break it into 4 parts. And it's kind of like when we talk about the distance of that a point goes on a transverse curve, right? We know what the amplitude is. For a whole period, 4 times the amplitude is how far you're going. And that's the same thing here, like this is the amplitude. Right, so you have amplitude, 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 gets us back to the original period. The block is, again, released from rest at the top of an incline. When it reaches the horizontal surface, it is moving with speed v naught. Now suppose the block experiences a resistive force as it slides on the horizontal surface. The magnitude of resistive force F is given as a function of V by F equals beta V squared, where beta is a positive constant with units kilograms per meters. I think I'm going to stop here because we're at about a half an hour for this one. And it's going to be another long integration, it looks like.